The first sentence reads, "The old man the boat," and you can see that you have some lexical ambiguity there. That's the old man, has a boat, or the old people in general go on board the boat. Or you might have syntactic ambiguity, like I convinced her children are noisy. So by the time you reach the word children, you believe, I convinced your children to do something, but then probably I convinced somebody else here that your children are noisy and so on. So there is some syntactic ambiguity going on. Now, many garden paths are as such, not just because of syntactic ambiguity on its own. It's just probably because there is some semantic ambiguity involved, and in particular, as far as semantic roles is concerned. So, for example, if you take this sentence, the athlete realized her goals, so we're over there, and we might say that probably goals over here is the patient to this argument, so the athlete realized her goals at the competition, okay? Or maybe, the athlete realized her goals were out of reach, so now goals is an agent to this particular verb, and the whole S bar over here is like the patient to this predicate. So it's not just syntax that leads to this ambiguity as we parse, it's also semantic roles that get to change as well over here. So humans probably do this, and I'm going to look at this example in a little bit more detail and convince you that this is useful, and we would like to model that. And this is what we're going to do in this particular work. So let's go. So we read the athlete realized. I'm going to be generating these so-called semantic triples for these, so which are shown over here. Realized is the predicate, it's the verb, so it goes up to, in this semantic triple in the last position. Athlete is the argument over here, so it's the, let's say, agent, or arg0, if we want to use Probang notation, which goes over there. So this is like a complete semantic triple. So the athlete realized, fair enough, but it's not just that. As soon as we reach the verb, we expect to see something else. So the athlete realized what? Realized, as we've seen in the example here, goal, so that something else is going to come up. So I'm going to be representing this ambiguity due to this incremental processing that we are doing in the terms of incomplete semantic triples as shown here below. So the predicate is over here, it's complete, but the argument here is incomplete. So I don't know what I'm going to see next. Is it like a verb? Is it going to be a noun? Is it to be, anything and go? And I might have multiple interpretations of what is going to come up next. So I'm just leaving here a set of compatible, let's say, roles, semantic role labels that correspond to this particular verb, this particular predicate. So this is like an incomplete semantic triple as far as the argument is concerned. It could be the case that you might have like a predicate incomplete semantic role triple with the argument here filled in, and we'll get to see some more examples later on. Okay, and then we go in and read a little bit more. So the athlete realized their goals. Good. So we find the argument here. We get to complete it over there. And now we're a little bit more sure. We believe that, goals is the agent of this predicate. So it's A1. So scrap the ambiguity and roles. Good. Yes? No. Because now that I get to complete reading the sentence, since a garden path, it's, things get to change over there. So now I have to update my whole belief over here for that semantic role triple. And now the argument, which used to be goals, now it's changed into the head of the subordinate clause, which is the verb where. And this is the agent, fair enough. And goals, which used to be the argument for that predicate, now becomes the argument for a different predicate. And it takes a different role as well. It's an A0, because it's the agent of that. So you get to see that as humans, we get to update these semantic role labels as we go along as well. It's not just syntax. Good. So just to give a little bit more of a definition for what we define as incremental semantic role labeling, it is the task where we get to determine semantic role labels as the input unfolds, word by word. So given a sentence prefix and its partial syntactic structure, so we can do work with that, we would like to identify arguments and predicates, it would like to assign correct row labels. So this will lead into those nice semantic role triples. But since we do this word by word and we have this incremental ambiguity, not all of these rows are going to be incomplete. These semantic role triples are going to be complete. Right, and just to give you an idea, this is kind of a easy example of why that would be necessary, would be interesting. So I just did that earlier today, and I went to Google and I tried to write a sentence, and for example, the criminal arrested, and what I get here as results is kind of probably it's based on a language model or something, and this is what you come up with, but it's probably not what we're expecting. So we are probably expecting the criminal arrested by, I don't know, a police officer, by something like that. So you get to see that the result that I'm getting here is actually about a Sims character, fair enough, but I was expecting to see something over here, which, I mean, it would be more informative if I get to see an A1 rather than the A0, and this is probably because it's the passivization of this, the criminal arrested by. I mean, this is fine, but probably it would be interesting to have here as a result something more. Whereas, for example, if you try something similar, I mean, the syntactically, well, it's an active voice here, so the police officer arrested, and you can see that the police officer arrested two burglars as the first hit, which is compatible. Okay, so they arrested something which is intuitive, okay, fair enough, and possibly because it's active voice, the engrams were far easier to get that and capture it. So it would be nice to try and use those semantic role labels incrementally and assist us in a sentence auto-completion task. Right, so so far people have been interested in doing a semantic role label for a full sentence. It makes sense, okay? So this is what people used to do, like, many successful pipeline approaches usually, such as the main tool, state-of-the-art results for Cornell 2009. And it's usually like a set of modules which is kind of classifying words as you go, provided you have the full syntax. It's usually based on dependency relations. So you have like, you first identify predicates, then you go and identify arguments, and then you get, because you have like semantic role ambiguity, you get to label them as you go along. So this is for a full sentence. Our way, the way that we're going to do it is going to be syntactic based. And we're going to use a variation of a tree adjoining grammar parser, which is called psycholinguistically motivated tree adjoining grammar, which is going to provide us with a full incremental and fully connected parse as you go along for each word. And since this is a lexicalized grammar, we are going to augment the semantic, we're going to augment the syntactic lexicon with semantic roles. And then we're going to feed these into the so-called incremental role propagation algorithm, which is actually going to emit semantic role triples, both complete and incomplete, as we go along for each word. Whenever we get to have role information, of course, some words don't have role information, obviously. And to further boost our results and our accuracy, we're going to feed it, as other people have done, the output of this algorithm to semantic role triple identifier and role label disambiguation and classifiers. Okay, so let's take things little by little. I'm not going to be presenting PL tag in full because this is like a whole different story, but just to give you a head start, as I said, it's a variant of tree adjoining grammars that supports parsing with incremental and fully connected structure, which means that you get to build prefix trees which are fully connected for every particular word that you come to get to parse. And why is this interesting? Why do we need like fully connected structures and them being incremental? So the reason is like, if you take a standard tree adjoining grammar derivations, they are not always incremental. So over here you have your lexicon, right? And your lexical enders may look like this, which is like, like CFG rules, or they can be like arbitrarily large treelets, let's say subtrees. And you might have like substitution nodes like this, where you get to put things in there, or you might have like auxiliary trees that get to modify some other parts of your prefix tree, of your derivation tree. So, for example, for the sentence "banks will take," you might process first the verb, which is in the middle, and then you will go and substitute over there on this NP the subject of it. Okay, so it goes first, even though it goes second, even though it's the first word, and then you will modify somewhere there in the middle the verb, so it will go banks will take. So we'll just slot in over there. It's nice, obviously, as a formalism, but it doesn't help us for what we want to do with semantic row labeling. So doing that incrementally, I mean. So instead, PL tag derivations are always incremental and full connected, and the way we do that is we take the original lexicon like this, and we further increase it with some sort of unlexicalized trees, which we call them prediction trees, which their only sole reason is to go and provide fully connected structure as we go along. So, for example, banks will take, okay, this is our sentence, so we start here with the NP, and then we go on and substitute this particular unlexicalized tree over the NP banks over here. So this is something that we get to predict. We haven't seen this yet, okay? There's no grounding as to what is going to be there, but we kind of anticipate that we're going to see verb later on. And you will get to see that, those nodes that belong to this particular prediction tree have those little ones over there, superscripts and subscripts. These actually correspond to nodes that we haven't seen yet, but we need further on some evidence, some actual elementary trees to go and verify those and say, this was what you predicted, but now you have the actual evidence for that. So banks, a verb I haven't seen yet, a verb structure I haven't seen yet. And I still haven't seen the verb, but I can now go and adjoin this slot, adjoin this modifier structure, and it become banks will, and then the VP we haven't seen yet. So you get to see this is further teased apart because you put this in the middle, but we are still incremental and we have a fully connected structure. And then the verb comes over here, we get to observe it, and PL tag has an extra operation which is called verification, which is doing exactly that. For all the particular nodes that you had predicted, you anticipate to see them, but you didn't have any particular evidence, go and find one of those trees in your lexicon which is compatible with that. So you see you have the AS, the NP, and the VP over here, they're over there, the ones that I'm showing in red. Go and replace those particular ones since it's fully compatible, and append any other structure that hangs right down below that. So take goes there, and you have the NP over here, and you move along. So this is what PL tag is doing for you. Now, the original lexicon obviously doesn't have any semantic information, just syntax. So what we want to do here in order to get done with this incremental semantic row labeling task is we are going to augment the original lexicon with semantic information. So we're going to be using, for this particular work, just verb predicates, which are derived from ProBank, and essentially what we're doing is like take all this particular notation and project it into the so-called integration points. So I will be calling those things again as integration points in the course of the talk. So what they really correspond to is like, this is, for example, is a modifying tree, okay? And this is like the auxiliary node here, it's the footnote. So I'm projecting the modifying semantic row labeling information here, and I put it on the integration point. So for example, you might have this structure over here, which is the prediction tree, which pretty much what it's talking about is like, I'm a verb phrase, I don't know what I'm talking about, I don't know what the verb is, but I'm kind of a template of a verb phrase, and I'm expecting here something with this NNP, okay, and has all these host of particular row labels. So you have like ambiguity over there. And this makes sense because you have a whole training set where you will have seen this particular tree or any other tree in different contexts. So in that particular context, that could be an A0, an A1, or this verb to take could be an A0 or an A3 on this particular NP node over there. So we take the original lexicon for PL tag and we augment it with semantic role information. And then as we go and as we go and process the prefix trees that are being output by PL tag, the main idea behind our incremental role propagation algorithm is that we want to emit either complete or incomplete semantic role triples, or even go and update them, either incomplete to try and complete them, for every integration point, either of the prefix tree or of the incoming trees that has role information in it. So for example, we begin here with banks, right? And then we put this we substitute in over there this prediction tree. Remember, it's because we haven't seen the verb yet, but this is part of the PL tag anyway. But this NP node over here, which is the integration point, okay, has some role information. So what our algorithm is really doing is making note of this particular node, which is the integration point, and then creates a triple, a semantic triple, which is, has the role information over there. And in this particular case, it's ambiguous. Okay, you have many roles because it's a prediction tree. And tries to complete it as much as possible. In this particular case, since the head of this particular integration point is banks, this is not a predicate because it's not a verb in this particular case, so it becomes the argument. And because we haven't seen the verb yet, this is an incomplete. So we go further on, and then we go and modify this because we do it incrementally. And this particular tree is bringing on some more information, so we go and generate another incomplete semantic row triple headed on the VP here. And then the verb comes, banks will take. Now, this is going to verify those nodes that we had predicted, but we hadn't seen them yet, and now we go and concretize them. So for every particular node, which I'm showing here in blue, we go and look up on the table all the incomplete triples that were there before and try to complete them. Here you have predicate information, so you go and complete the predicate information, so now it becomes a complete triple. And since you had a lot of ambiguity because of the prediction tree as far as semantic roles was concerned, just because your tree here is more concrete, it has been seen in less context, we can safely say, you know, ignore those things that were ambiguous because of the prediction tree, just use A0 and A3. And yeah, because we introduced a new node with role information and yet another incomplete triple, which goes on and gets completed from this particular lexicon entry. To complete the sentence, banks will take measures, so you can complete that as well. Right, and just because you know, these semantic triples have ambiguity, and because our algorithm gets to overgenerate stuff, and it makes sense because you have these prediction trees and so on, we just feed it into a classifier which is based on my lexical features, syntactic features, to just decide, you know, I have this particular new semantic triple. Should I keep it or not? And if we decide to keep it, then we go and disambiguate these particular cases which have ambiguity in roles with a multi-class classification problem. It becomes a multi-class classification problem, and then we just decide that this is the full complete semantic role triple. Right, experiments. So as I said, we just use propositions with verb predicates only for this particular work. And just because we wanted to test our ability to do semantic role labeling and not syntactic parsing as well, we just stick with the gold lexicon entries during parsing. So this is similar to what you would have with ConLL SRL only task, which is using the gold standard dependencies, okay? Now for evaluation, I will present you, and we measured full sentence accuracy, which means what happens when we reach the end of the sentence. Have we done a good work? But since it's really the incremental part we would like to see if we're doing well, I will also be reporting unlabeled prediction score, which is actually the number of complete and incomplete triples that get to predict correctly for every particular word. So essentially, this is going to be shown as a graph, okay? Right, so system comparison. Our model is over here, ISRL, which is using all semantic row labels. So remember, we had ambiguity in those particular nodes. In order to find kind of an upper bound for this, I will also be comparing on ISRL, or what we call ISRL Oracle, which is just using the gold standard semantic row labels. So let's see, you know, how well is our algorithm doing if you just scrap this, you know, ambiguity over there. And then we compare against the majority baseline, which is just a simple set of heuristics to do argument identification. And for doing the labeling disambiguation, we just use the majority dependency class for that particular label. So the argument has a dependency relation given from ConLL data. Take the majority class for that. So an N subject should be an A0, an object, direct, indirect should be an A1, and so on. And a slightly variant of this is the mold baseline, which is pretty much the set of heuristics for identification. But for role disambiguation, you use the majority class based on the mold parser output for dependencies rather than the gold standard dependencies. Right, so for the full sentence scenario, we are over here. We kind of get to beat both baselines, which is a good thing. And it makes sense because we get to make use of this prediction thing to do more of these incomplete triples and complete triples. We lag behind the Oracle which also makes sense because you had this ambiguity over semantic roles, so your classifiers probably are not doing a very good work over there. And then, obviously, mode baseline is below the majority baseline because you have problems with your dependencies. And in this graph, what I'm showing you is the unlabeled prediction score, which is, remember, per word. And in order to be fair for, for these comparisons, I've only taken words which are 20 words long, and I'm presenting you here the UPS score for each particular word. So green is where our model is, and this is the Oracle and the rest systems go below. So we can see again the same trend. We are above the baselines, below that one. But the good thing is that it's fairly straight as a line, which means that we get to compute in complete triples as we go along early in the sentence, and then as we later go on, we get to complete them also correctly. Otherwise, that would have gone over there down, so it would nosedive. It's a good thing. It means that we're actually predicting things well. So, to conclude, I just presented you a new task of incremental semantic labeling, which is based on the psycholinguistically motivated tree adjoining grammar. It's a syntax-first approach, and the PL tag has a lexicon. We augmented with semantic role labels, which come from a probe bank. We introduced this incremental role propagation algorithm, and in order to boost our accuracy, we use a classifier for identification and role disambiguation. And it's shown to outperform baselines, and it also does quite well when we do things incrementally, as I showed you in the last graph. And the code is available. You can have a look at it if you like. Hopefully, use it. Thank you.
Do we have any questions?
Thank you. So your example, your motivating example, the semantic ambiguity was entirely derived from the syntactic ambiguity. Is that correct?
Yeah, it's kind of a joint thing, yes.
Yeah, or it's a joint
sure,
part.
Yeah.
Are there any examples where there's a semantic ambiguity that is not a standard syntactic ambiguity, or is that not something you're targeting here?
It's not something I can think of the top of my head. It could be based on, let's say, semantic ambiguity, which, which has to do with the grounding in a particular, let's say, word, okay? So that could possibly be something. I mean, if something is more like of a patient rather than an agent, but the syntax is entirely the same, it could be, if it's like I'm manipulating an object rather than a person, so it could be an A1 or an A2, for example. So the syntax should be the same, but the label should be different, but probably the structure also remains the same.
And just to comment on that example, also the predicate actually is ambiguous because the two sentences, the realize is a different predicate. It's a different meaning of realize.
That's true. Yeah. So semantics also has to do with predicate, of course. Yeah. Of course.
Where did the tree adjoining grammar come from?
Sorry?
Where did you get the tree adjoining grammar? Was it extracted from the Penn Tree Bank?
Yes, exactly. Yeah.
So are you keeping some kind of a beam, or do you just have one candidate as you're going through the sentence? I'm just wondering how that UPS score is calculated.
So no, we're always taking the top derivation in this case, but the parser itself is keeping at least, so it has a beam on its own. But we're always speaking for every particular word, we're always speaking the first one. So yeah, that's the one on the graph. That's a good comment.
The Oracle best, or the highest score?
The highest scoring.
Highest score. Mm-hmm.
One sort of high-level question about the motivation. Aside from the psycholinguistic thing that we humans do it, is there sort of a practical setting where you are needing this, or is it more just to see how far we can get?
Well, I guess that the original motivation is just psycholinguistic, to be honest. But it would be interesting to try and apply it. I mean, I don't know whether Google is actually using any of these or is planning to use that thing. But you could possibly autocomplete something better in this sense.
Yeah, I mean, I guess then the follow-up question is, how fast or slow is it?
The algorithm is actually quite fast. The parser is probably the one that's slowing down things. But you could, that doesn't mean this is the only format you can apply it, right? So you can bolt it on anything pretty much.
Sure. Cool. Let's thank the speaker, and
Thank you very much.
so that completes the session. Enjoy your coffee, and the next session will resume in half an hour.